Hey guys, today we're talking about solving all polynomial equations. Now, the past few chapters we've looked at factoring polynomials, and we said that we can take those individual factors, set them equal to 0, and solve for x. And the value that we get is actually known as a 0 or a root of the polynomial. Well, today we're going to dive a little bit deeper into that. But before we do that, let's take a look at some terminology. Now, you've heard me mention double root or multiplicity in class here the last few days. Essentially, the multiplicity of a root is just the number of times x minus r is a factor of our polynomial. So we might factor a polynomial and see that x minus 1 is not just a factor once, but twice or possibly 3 times. So we say that that multiplicity of that factor or that root is 2 or 3 or however many times it appears. Now, there's a number of roots of a polynomial theorem, and it goes like this. It says every polynomial of degree n has exactly n roots, including their multiplicities. So if I had a cubic polynomial, then there must be exactly 3 roots. If it's a degree 4 polynomial, there must be exactly 4 roots. All right, finally, we have the fundamental theorem of algebra. And don't be fooled by the first 3 letters. It's not that fun. Anyways, it says every polynomial equation, p of x equals 0 of degree n greater than or equal to 1 with complex coefficients has at least one complex number solution. Essentially says this: if you have a polynomial, p of x, it's got a degree greater than or equal to 1, it's going to have at least one complex number solution. All right, we got 3 graphs down here, and what we're trying to illustrate here is just the difference between 1 real solution, 3 real solutions, and 2 real solutions where 1 has a multiplicity of 2. So here is a cubic polynomial. It has degree 3, so there should be exactly 3 roots according to my number of roots theorem. However, I see that it only crosses the x-axis once. So this is an example of 1 real solution, and the other 2 will be imaginary. All right, now the next one, you see that this is also a cubic polynomial. It's going to have degree 3, so there should be 3 roots. In fact, there are 3 real roots. You can see that by seeing how it crosses the x-axis 3 times. Finally, we have another 3rd degree polynomial, so there should be 3 roots. However, you see that it only touches the x-axis twice. Once it passes through, and the other time it touches it, bounces off, and comes back down. Well, this is what the visual representation of a root with multiplicity of 2 looks like. Anytime we have a multiplicity of 2, it's going to bounce off that x-axis at that point. All right, let's take a look at a few examples for today. Here's our first one. It says to graph the polynomial function p defined by x to the 5th, yada, yada, yada. Well, I've gone ahead and done that in Desmos, and you can pause the video now and do that in your graphing calculator or in Desmos, either way. And here's the graph that we get. So you see that it's going to have these 2 bends in it, and it looks like we got these x-intercepts here at negative 1.1, negative 0.2, and then 2.8. So we're not going to take a ton of time and care in graphing this. We're going to kind of get the gist of it in our graph. So we see that this is going to come up, come back down, and then come back up again. Now, obviously, you'd take a little bit more care in your graphing, but for the sake of notes, we're just going to wing it. All right, so here's our negative 1.1, here's our negative 0.2, and here's our 2.8, if those were the actual roots. It says, how many real zeros does p have? Well, the number of real zeros is the same number of x-intercepts. So we say it's going to have 3 real roots, and this is, again, the same number as x-intercepts. All right, and it says, how many non-real complex zeros does p have? So the non-real part is the imaginary. And we know because I got a degree of 5, there has to be 5 total roots or solutions. And since 3 of them are real, that means the other 2 must be imaginary. All right, let's try another example very similar to that. It says consider the polynomial function p defined by x to the 5th minus 7x cubed plus 15x squared plus 1. So again, I've gone ahead and graphed that in Desmos for us. I'm going to turn this graph off, turn that one on, and kind of just get centered there a little bit. We'll zoom in, and you can see here that it crosses the x-axis at negative 3.3, goes up, comes back down, and gets really, really close, but doesn't bounce off the x-axis. It passes through the y-axis here at 0 over and 1 up, and then continues up. So again, just kind of for simplicity and quickness sake, we'll do a quick sketch of what that graph looks like. It's going to come up, come back down, run along there, and go back up again. All right, so it says how many real zeros. Now the real zeros, again, are the number of x-intercepts, so this is going to have 1. And then how many non-real complex zeros will it have? So again, it's got a degree 5, which means there must be 5 roots. So if there's 5 roots and one of them is real, that means there must be 4 that are imaginary. All right. In example number 2, we are asked to give the degree of the following polynomial and find all zeros and their multiplicities. So here's an instance where we have a polynomial. It's in factored form. So remember how to find our factor, or find our roots from our factors. We're going to take each one of the factors, set it equal to 0. So I'm going to get 1 when I set that first one equal to it. X plus 9 needs to be set equal to 0. When I move that over, I get negative 9. And then I'm going to take my 2x minus 5, set that equal to 0, add my 5, and divide by 2. So I get 5 halves. Now let's talk about their multiplicities. Their multiplicities can be seen as their exponents. So the exponent on the factor x minus 1 is 1. The exponent on x plus 9 is 3. So I say my negative 9 has multiplicity, see if I can spell it right, of 3. While negative, 1 and 5 halves have multiplicity of 1. And we'll abbreviate multiplicity there. All right, p of x equals x plus 1 to the third, x plus 20. You're getting good at finding these zeros now. Really, it's just the opposite value. And therefore, I got negative 1 and negative 20. Those are my roots there. My degree of this polynomial, oops, I forgot to do the degree of that part A here. So my degree here, again, if I add my exponents, I got 1, 3, and 1. My degree here should be 5. Yes, my degree should be 5. All right, so here I got degree 3, degree 1. So here my degree should be 4. I'm going to add those exponents across. And now I have x plus 1 is going to have my multiplicity here of 3. And then my negative 20 will have my multiplicity of 1. All right. Let's do one final example here for today. It says, give an example of a polynomial function in factored form, that's nice, that has 3 as a root with multiplicity 4. So we'll take our polynomial p of x, and I want it having, that has 3 as a root. So that means x minus 3 must be a factor. It's got to have multiplicity of 4, so that means the exponent needs to be 4. And I can throw another factor in there just for fun. Let's throw in x plus 1. And then how about 2x minus 3? So here is a polynomial in factored form that has 3 as a root of multiplicity of 4.